I got a request from a student to go through an A-level maths differentiation question. So this is actually taken from the C2 syllabus and it's on applications to differentiation. But even C1 students can benefit from this video tutorial as well, because I'll be going through the basics of differentiation. Okay, so I've got a handful of questions here, but I'm only going to go through this one here. So the one I've highlighted, the one I've put a red box around, and the question says, a farmer has 100 meters of fence available with which he intends to build a pen for his sheep. He intends to create a rectangular pen against a permanent stone wall. So if you have a look over here, this is the stone wall, and we have a rectangular pen. So when this student sent this through, she didn't capture the whole diagram, but you can imagine what it's going to look like. So you've got this is your length of the rectangular pen, this is the width, which is X meters, and then you're just going to have another length going up there up to the stone wall, and that would also be a length of Y. Okay, the question says find the dimensions X and Y meters so that the pen has the maximum area. Okay, so as it's amongst a stone wall, what this means is there wouldn't be any fence along this stone wall here. I mean, there wouldn't be any point. I mean, what's the point having a fence here if you've got a stone wall there? I mean, that's where the barrier is. The stone wall itself is a barrier. So this bit here is going to be the fence. It's just going to be this length here, which is the Y, and then across, which is X, and then up to the wall, which is Y. So those three added together must equal to 100, because if you look at the first sentence, or the first part of the sentence, it says a farmer has 100 meters of fence available. So what that means is I can create an equation or set up an equation just based on that fact alone. So remember, we only have the fence is just Y going down, X meters across, and then Y up. So we have Y add X add Y, or we have 2Y plus X is equal to 100 meters. Okay, as I was saying before, there's no point having fence along this side here, because this is the stone wall itself. This bit here, which I just shade in, is the stone wall. So that is the protection for the sheep. So that's the barrier for the sheep. So there's no point putting fence. So the fence is only Y add X add Y, which is 2Y add X, which is equal to 100. Okay, so what we need to do is we need to maximize the area, because that's what the question says. It says to maximize the area. So the area of this particular pen is just going to be the length times the width. So if the area is A, that means A is equal to X times Y, which is just XY. Okay, so we need to maximize A with respect to these two variables, but the only issue is we can only differentiate an equation in one variable. We can't have two variables here. These are two variables. We have X and Y, which can represent any variable, or they can be any value. So what we need to do is we need to eliminate one of these variables. Okay, so if you think back to GCSE, where we had simultaneous equations, you had two equations, both in X and Y, and what you would typically do is take one of the equations, rearrange it to make either X or Y the subject, and then you would substitute it into the other equation. And what you effectively do is you eliminate one of the variables. So we're going to do the same thing here by using this first equation. So remember, the only way you can eliminate a variable is you need a secondary equation. So we use this equation here. Remember, this is the fence, the length of the fence. So we use this here to eliminate. We can eliminate one of the two, but let's just eliminate the Y in this equation for the area. So what we need to do is we need to rearrange this so Y is the subject. Okay, so to rearrange this, what we do is we bring the X to the other side, and then we divide by 2. So what that gives you, it gives you Y. So what I'm going to do is I'm just going to skip a step out here, but if you were to rearrange this first equation, the equation that I've underlined here, if you rearrange it to make Y the subject, you would first subtract an X onto the other side and then divide by 2. So what that'll give you is it'll give you 100 minus the x all divided by 2. Okay, and what I can do is I can just partition that fraction. So I'm just going to separate it into two terms. So what we'll have is we'll have 100 over 2 minus x over 2, or we'd have 100 over 2, which is just 50, minus x over 2. Right, so using this second equation here, and now that we've made y the subject, what I can do is I can substitute this into our equation for the area, and that would eliminate the y. And then we can proceed to differentiate. So just remember that we can only differentiate in one variable. So substituting this into the formula for the area, we'll get a is equal to x, that's the first x there, multiplied by y, which is, and y in itself is 50 minus, okay, what I'm going to do is I'm just going to bring this over 2, I'm going to bring that out and put it in the front. So remember, dividing by 2 is the same as multiplying by a half, so you should get half times an x. Okay, so before we differentiate, what we want to do is we want to expand this out. So just multiplying the term on the outside by each term on the inside. What we'll get is we'll get 50 times x, which is 50x, multiplied by, well, we have x multiplied by minus a half x, which just gives you minus a half stays as it is, and then you have an x times an x, which gives you x squared. Right, so what we've done is we've eliminated that y variable and we're just left with an x, so now we can differentiate it. So remember, this is like a function in x. Think of a and x as a function, so you substitute values of x and you get your output values of a, or you substitute different values of x and you get different values for the area. So you can think of this as a function, and if you were to draw a sketch of this, it would look something like this. So what I'm going to do is, where should I place this? Okay, I'm going to do it up here in the top left corner. So what it would look like is it look something like this. Okay, notice that it's a minus half x squared, or it's a minus x squared graph. So what that means is it's an upside down U shape. So what it will look like, it will look like something like this. So this is your, so as a replaces y here, this would be your a going up there, and this is your x. So it would look something like this. So it'll come up, remember it's an upside down U, so it'd be something like this, and then it'll come down again. So as you can see with this small sketch up here in the top left hand corner, you know, you'd expect to get a maximum. You have one maximum value there. So that's the value we're trying to find. That is that, what is that value of x which maximizes the area A? So okay, in order to do that, what we need to do is we need to differentiate. So remember, when we're differentiating, okay, so as it's with respect to a, what we have is we have dA by dx. Okay, so remember, to differentiate, what you're doing is you're bringing the power in front of the x, multiplying by the constant, and then reducing the power by 1. So here, if we go back to this equation, remember this is just to the power of 1. So what you'll get is you'll multiply that 1 comes down, multiplies with the 50, which just leaves you with 50. And then you do 1 minus 1, which is just 0, but then anything to the power of 0, so x to the power of 0 is just 1. So that just disappears, leaving you with 50. Okay, so same again here. What we do with the second term is this 2 comes down and multiplies with the half, and that effectively cancels out. A half times 2 is just 1. So that disappears, and we reduce the power by 1, which is just going to be 1. So what we're left with is we're just left with minus 1x, or just minus x. So that is the first derivative of this function is. So this function a is equal to 50x minus half x squared. Okay, so remember, at a maximum, so at a max, remember this first derivative, so let me just write this down over here. So at So at a max, dA, so dA by dx, so dA by dx has to equal to 0. Right, so this has to equal to 0, because remember, if you go back to our diagram here in the top left hand corner, at this point here, the gradient is 0, isn't it? So remember, think of this as the gradient function. So this allows you to find the gradient at every single point along this curve. So remember, at the maximum, the gradient is 0. So remember, and that's what we're trying to find. We're trying to find that maximum value here. So we just need to solve 50. Well, if dA by dx is equal to 50 minus x, we just need to solve 50 minus x is equal to 0. So we're looking for that x value which gives a gradient of 0. And that is just simply going to be, if you move that x to the other side, that gives you a positive x, that x has to be 50. So x is equal to 50. Okay, so remember, when you take the first derivative, remember, it doesn't necessarily tell you whether it's a minimum or a maximum. It's only because I've actually drawn this graph out here, you can see clearly, based on this function over here, a is equal to 50x minus half x squared, there can only be one stationary point, and that is of course a maximum. But what you can also do is you can take the second derivative. So if you were to take the second derivative of this, so by using the same rule again, so if you've done d squared a, I don't know if you can see that, but that's actually a d squared a over dx squared. Okay, so that is simply, well, we only got one x term here, it's just a minus x, and that will just leave you with, if it's x to the power of 1, the 1 comes in front, multiplies with the minus 1, and the x effectively cancels out when you reduce the power by 0. So this is just minus 1. So the second derivative is minus 1, and remember, for it to be a maximum, this second derivative has to be less than 0. So, you know, this just proves to you that, you know, any stationary points on this curve is going to be a maximum. So this is the value which maximizes the area. So if x is equal to 50, that means, well, if we go back to, well, when we use the length of the fence, remember the length of the fence is 2y plus x equal to 100. Well, when x is equal to 50, y will be equal to, well, 50 minus x over 2. If x in this case is 50, we know that the x value has to be 50 in order to maximize the area. The y value is going to be 50 minus 25, because x over 2 is just 50 over 2, which is 25. So when x is equal to 50, y is going to equal to 25. And those are the two values which maximize the area of this rectangular pen. So remember, the area, to maximize a, the x value has to be 50. We proved that earlier on by using differentiation, and the y value is, well, using this equation here, because remember, it also has to satisfy this equation up here, because remember, the length of the fence has to be equal to 100, so 2y plus x equal to 100. We know that to maximize the area, x has to be 50. So when x is 50, that means y has to be 25. So the area is going to be equal to 50 times 25. And that is just simply, well, 50 times 25. A quick way to do that is to multiply 25 by 100 and then half it. And what that would give you is, that would give you 1,000, well, if you think 25 times 100 is 2,500, halving that will give you 1,250. Okay, also notice that the units of the answer is actually meters, because all these dimensions are in meters, and also a is in meters squared, so this will be meters squared. And that is the answer to this question. So just doing a quick recap. So the area is equal to x times y. We know that because it's a rectangular shape. But the problem is we can't differentiate this because it's in two variables. So what we need is, we need a second equation And you notice how they've actually told you about the length of the fence being 100 meters. Well, that allows you to create the second equation, because by creating this second equation, what it does is it allows you to eliminate one of those variables. You see down here how I use this equation to make y the subject, and then what I did is I effectively got rid of that y variable by substituting this in. And then what you're left with is you're left with this equation down here. So a is equal to x, and then in brackets 50 minus half x, and now we can actually differentiate it. So once you multiply everything out, you differentiate it once, and what you do is you need to solve that for 0, because remember, at a max, and I've got it written on the left hand side here, at a max dA by dx is equal to 0. And just before doing that, I actually drew a sketch of this graph here, because remember, think of this like as a function. Yeah, so you substitute values of x in. That's the x for the length, well, the width of this rectangular pen. You substitute different values of that in, and that obviously adjusts the area, that affects the area. So but there is a particular point there which actually maximizes it. It gives you the highest a value, and that is when x is equal to 50. And when x is equal to 50, going by this equation for the length of the fence, y has to equal to 25, and that will give us our maximum value for the area.